Fusion Mobile, quality e-learning experience on the go.
You're welcome back to the class. Our topic for today is captioned sets. All right. A set is a well-defined collection of distinct objects. The objects that make up a set is called or are called members of a set. Some cases you see people call them elements of a set. Elements of a set. Okay. Sets are comprised of members or elements. All right. They could consist of numbers. Sets could be numbers. It consists of numbers, letters of the alphabet, They could as well be people or names of people. And so on. Okay. Elements in a set are always enclosed in a curly bracket. Curly brackets looks like this. Okay, you could enclose your numbers. Okay, or you could enclose your alphabets A, B, C, D with a curly bracket and so on. All right. We have some definitions to make, some properties we have to define for you to understand the concept of set. We have to make the following definitions. The first thing we'll have to define is equality of set. Equality of sets. What we call equal sets. Equal sets. Here, two sets are said to be equal if and only if they have the same elements. Okay, we can take for example set A comprised of numbers 1, 2, and 3, and set B comprised of numbers 3, 2, and 1. You find out that all elements in set A are the same elements in set B, and so we can say that therefore set A is equal to set B. We should note that arrangements in a set does not necessarily matter. Arrangements in a set does not necessarily matter to denote whether sets are equal or not. So just like you can see in set A, arrangement follows 1, 2, 3, and in set B, arrangement follows 3, 2, 1. But the most important thing are just that elements in the sets are the same. We have to talk about another property, subsets. Let's talk about subsets. Okay, let me complete my notes. I said arrangement of elements in a set, of elements in a set does not really matter. All right, so the next thing I want us to talk about are subsets. A set is a set, assuming we take set A like in above. A set A is a subset of a set B if everything in A is also in B. Alright, a set A is said to be a subset in set B of a set B if everything in A is the same thing in set B. Alright, so just like above, we have A to be equal to 1, 2 and 3 elements, and B is comprised of elements 3, 2 and 1. Alright, we can say that A is a subset of B because both contain the same elements. Over to the next slide, we have to define what we call power sets, power subsets. A power subset occurs if only every element in a set A is also contained in set B. If only elements in set A also occurs in set B, and then there exists one or more elements in set B that are not in A. That means if all elements in set B are in set A, and then in set A, in same set B, there are elements in set A that do not occur in B, then we say that the set is a power set, a power subset, sorry, rather. And so we take examples like this. For example, if set A is just made up of elements 2 and 3, and set B is made up of elements 3, 2 and 1. Okay, good. We can say that set B is a superset, it's a power subset of A, and hence A is a proper set of a proper subset of B. Sorry, talking of proper subset. Alright, so therefore we can say that B which is made up of 3, 2, 1, just like above, and A made up of sets 2 and 3. Therefore A is a proper subset of B. Alright, we go over to defining null sets. Null or empty sets. Alright, this set contains no elements in it, not even 0. So even 0 is an element, so if 0 occurs in a set, then it's not a null set. Null sets are denoted with curly brackets but showing no elements inside it, even 0. Alright, you need to note this, that an empty set, you need to note that an empty set is a subset of every set. An empty set is a subset of every set. Okay, now we go over defining types of sets. Types of sets. We have two types of sets. We have, number one, we have finite sets. Finite sets, number one. And number two, infinite sets. Alright, a set is said to be finite if you can list all its elements. It is also called countable set. Okay, countable set. Meanwhile, a set is said to be infinite or uncountable when all of its elements cannot be listed. Alright, uncountable. We have examples of sets that are finite and sets that are infinite. We can take some examples over to the next slide. For finite sets, we can take, for example, a finite set. We have examples like a set of all the alphabets. A set of all the alphabets is a finite set. All the alphabets. Okay, that's my curly brackets. Or you can as well take other illustrations like a set of shoes a student have. A set of shoes a student have. All these and many other examples comprise of what we call a finite set. And then for infinite sets, we have some examples like a set of all positive integers. A set of all positive integers. There are other examples that come to mind, but we'll stop at this. We'll save some time. Alright, the next thing we'll be talking about is the Venn diagram. The Venn diagram, because in the course of this study we'll be going through examples using Venn diagram. A Venn diagram. Alright, a Venn diagram is a pictorial representation of the relationship between sets. Here the sets are represented in shapes, usually circles or oval. Okay, the sets are represented in shapes, could be circle, that it's not perfect, but we can manage that. It could be oval shape. Alright, and the elements of the sets are labeled within the cycle. For example, if we have a set of days, our example, we have a set of days. Arrow is defined as the set of days. You have Monday, okay, and then you have Tuesday and Wednesday. Then we can represent the set arrow pictorially as shown below. Okay, so that you have Tuesday, you have Monday, and then you have Wednesday. Alright, this gives a pictorial depiction of the set R. Okay, we can take some other example, but this looks a bit complex, but happy will you be if you do understand it. Example 2. Alright, maybe you're given a set, Q. Where you are told that x is or x are values such that when you see this two dotted sign, it is read as such that 2x minus 3 is less than 11. Okay, you have to solve this inequality to obtain the actual value of this, and the solving follows mathematically just like your normal algebra. And so from this point you can say that 2x minus 3 is less than 11. You can take minus 3 over to the other side, and so it becomes positive. Alright, 2x is less than 14, so that x on its own will be less than 14 over 2. Okay, all I did was to divide all sides by 2. Here was 2x, and then so that x will be less than 7. Okay, and so all we are saying is that cure is such that x, what are the elements x now? Integers less than 7, and integers less than 7 include 0, 1, 2, 3, 4, 5, and 6. Alright, and so you can represent this pictorially. I still have space here, so I could write q at this point, and then my cycle follows, making my Venn diagram, and I have elements 0, 1, 2, 3, 4, 5, and 6, okay, to be elements of the set Q. Alright, next we'll be talking about a universal set. Universal set. Alright, it is denoted as capital U or capital E. Okay, a universal set is a set of all elements under consideration. Okay, a set of all elements under consideration. It is often denoted by capital letter U or sometimes capital letter E, just like as you can see on the screen there. For example, maybe you are given a universal set, U to be equal to sets of numbers ranging from 5, 6, 7, 8, 9, 10, 11, and 12. Alright, and you are given elements in another set A, X, such that X is a factor of 60, and then B, such that X is a prime factor, okay, a prime number rather. Okay, all these are to be picked relative to the universal set, as you can see. So how do we pick factors of 16? Factors of 16, that means A will be X, such that factors of 16 here includes 8. Okay, that's the only factor. And then B, set B will be comprised of X, such that we have prime numbers. Prime numbers we have there include some 5, 7, and 11. Alright, so we picked all these values relative to the universal set. Okay, next thing we'll talk about is complements. A set of elements in a given set that are not in another given set are called complements. A set of elements in a given set that are not in another given set but are in the universal set. Okay, they are not in another set but they are contained in the universal set. They are called elements. Alright, we'll take instances as we usually do. Okay, from the previous example we did, we found that the set A such that x is a factor of 16 is 8, and then the set B such that x is a prime number consists of 5, 7, and 11. So we have that a complement is written this way. Okay, will be elements in the universal set but are not in A. Elements in the universal set but are not in A are 5, 6, 7. We wouldn't write 8 because 8 is in A. 9, 10, 12, 11. And then B complement we can write as elements in B but are not in the universal set. They include, there you have 6, 8, 10 and 12. Right. Next we'll be talking about operations on set, or we titled set operation. Set operations. In sets we have intersection of two sets. We have intersection of three sets. We have complement of an intersection. Right, and then we have union of sets. Of combined operations. Right, and then drawing of Venn diagrams as illustrated previously. De Morgan's theory. Alright, for the course of this class we'll stop at drawing of Venn diagrams and resolving them too, because De Morgan's theory leads to a higher level of this set theorem. Alright, we start off by talking about intersection of two sets. Intersection of two sets. Now two sets X and Y are said to intersect such that elements that are common to both sets can be distinguished. Alright, assuming we have sets X and Y, you know, the intersection X intersection Y is a set of elements that are common between the two sets. Is a set of elements that are common between the two sets. Okay, and it's denoted as X intersection Y. For example, assuming we have set X such that it has elements 1, 2, 5, 6, 7, 9, and 10, and then we have set Y such that we have elements 1, 5, 6, and 10. Therefore, X intersection Y, elements in X that are also in Y will have 1, we have 5, and then we have 10, and then we have 10. Pictorially, this can be represented with the Venn diagram as follows. Okay, we have two cycles denoting the two sets, and then here forms intersection 1, 5, 6, 10. Alright, and then elements that are not in both are denoted as follows. Elements that are not in both are denoted as follows. You have 3, 4, 8 as Y, and then you have X as 2, 7, and 9. Alright, here our Y should have been Y equal to 1, 3, 4, 5, 6, 8, and 10. Alright, so you find out that the points of intersection are 1. Okay, you have 1 here too, you have 5, you have 5 here too, you have 6, you have 6 here too, and then you have 10. Alright, and so this is a Venn diagram. Let me make it look better. Okay, this is my cycle. This is Y, set X, and this is the universal set. And so I have 2, 7, 9, 1, 5, 6, 10. Okay, at this point I have 3, 4, and 8. We can take another example to illustrate this better. Example 2, a set X with elements 1, 6, 9, and a set Y having elements 1, 3, 5, 6, 8, and 9. Alright, X intersection Y will be equal to set of 1 and 6 and 9. You see, at this point we can as well say that X is a proper set, is a proper subset of Y. Okay, so the representation takes the following shape. So you have this, our oval shape, and then you have another shape inside the cycle since it's a proper subset, and then you have 1, 6 and 9, and then you have elements that are not in set X but are in set Y. Set X, set Y, and those elements include 3, 5 and 8. This is still my universal set. Alright, we're talking about union of sets. Union of sets. The union of two sets A and B is the set of elements which are in A or in B or in both. Elements which are in A or in B or in both A and B, and so union is denoted with the symbol this, not necessarily a U. Alright, for example, given the sets of values such that the universal set U is equal to 1, 2, 3, 4, 5 and 6 and 10, and then I close my set. Alright, X is defined such that 1, 2, 6 and 7 are elements, and Y is defined such that 1, 3, 4 and 5 and 8 are elements here too. Alright, X union Y will be equal to elements that are both in the two sets being joined together, and so X union Y will be equal to joining the two sets together without repetition. So you have 1, 2, 3, 4, 5, 6, 7 and 8. Alright, so this can be represented in the Venn diagram as follows. Alright, this is my cycle to denote set X, and this is my cycle to denote the set Y. 1 occurs in both sets, and that seems to be the only intersection point. And then joining the two elements, you have 2, 6, 7 on set X, and on set Y you have 3, 4, 5 and 8. So my universal set, this is X and this is set Y, and the element in the universal set that is not in both sets, you can see it here, element 10. Alright, you should note that if X is a subset of Y, if X is a proper subset of Y, then X union Y will be equal to Y. Alright, Let's illustrate this. Let's illustrate this using the example below. Okay, given that a universal set U is equal to, or is defined as 1, 2, 3, 4, 5, 6, 7, 8, and 10 as our universal set, and then X is defined to have elements 6, 1, and 9, and Y is defined such that elements 1, 3, 5, 6, 8, and 9 are contained in Y. We shall find X union Y and draw a Venn diagram to illustrate that if X is a proper set of Y, then X union Y is equal to Y. Alright, therefore X union Y will be equal to 1, 3, 5, 6, 8, and 9. Representing this on a Venn diagram, we can draw as follows. Can draw the Venn diagram as follows. Okay. The elements 1, 6, and 9 inside set X, and Y with elements 3, 5, and 8. Elements that are in the universal sets but are not in both sets X and Y are 10, 2, 7, and 4. This is my universal set. Hence, this illustrates that since X is a proper subset of Y, then X union Y is equal to Y. Next, we'll be talking about complements of the union of a set. Complements of the union of a set. Complements of the unions of set X union Y is a set of elements such that are members of the universal set but are not members in the union of the two sets. They contain elements that are members of the universal sets, but those elements are not contained in the union of the two sets. Okay, what we are saying is that we're talking of elements in X union Y when you unite the two sets, but they are not contained in the universal sets. But not in the universal set here. Okay, this could be a rough depiction of what I have in mind, but not the correct form of doing it. Alright, complements are denoted as A union X union Y with a stroke, or you can as well write as X union Y, denoting a C as a superscript outside the bracket. Alright, we illustrate using examples. We use the following example. Example 1. Okay, given that the universal set U is equal to my curly brackets 1, 2, 3, 4, 5, 6, 7, 8, and 9. Alright, and then you are told that set X contains elements 1, 2, 6, and 7, and set Y contain elements 1, 3, 4, 5, and 8. The set X union Y will be equal to having elements 1, 2, 3, 4, 5, 6, 7, 8, having both elements in the two sets X and Y without repetition. Hence, X union Y complement, which we can write as well as X union Y C. Okay, elements that are in X union Y but are not in the that are in the universal set but do not occur here. Okay, it's a difference of one element, which is 9. Alright, you can see that while we do the representation on the Venn diagram. Okay, alright, this is our Y and this is our X, and this is the universal sets, and you have 6, 2, and 7. Okay, the two sets have one element in common, which is 1, 3, 4, 5, and 8. The only element left out there is 9, because it is contained in the universal set but not in the union of the two sets X and Y. So we say this is X union Y complement.